Okay, exponents are used to represent repeated multiplication. Multiplying the same base number over and over again. Yesterday we defined some vocabulary words that we're going to see in this lesson today. Base was one of them. The base is going to be the big number. So typically when we're working with powers and exponents, you have a big number and then you have a little number. You have a little tiny. Okay, so the base number is the 3 in this example, and the 5 is the exponent in this example. So the 5 is telling us how many times the base is being multiplied together. The number 3 is the number that we're multiplying repeatedly, okay? So whenever I expand out what this actually means, it's going to look like this. 3 times 3 times 3 times 3 times 3. It does not mean 3 times 5. It's very different. 3 to the power of 5, or 3 to the 5th power, is 3 times 3, which is 9, times another 3, which is 27, times another 3, and then that answer times another 3. Very different than just 3 times 5, which is 15. Does everybody understand the difference? Okay. At the bottom, we have some examples. We're not solving any yet. All we're doing is just expanding them or showing what it's going to look like as the power. Okay. So I have 4 to the 3rd power. Is there a different way that I could say that, Holly?
4 times 4 times 4.
4 times 4 times 4 would be expanded. So I can read this number 4 to the power of 3 or 4 to the 3rd power, but I can also say 4 cubed. Okay, whenever you started doing volume last year, you can sometimes write your answer in cubic units or meters cubed or centimeters cubed. When you have a little 3 as your exponent, you can say cubed. Okay, what about the next one? How would I write that one? What would it look like, Deacon? 3 to the 4th power. If I expand out the next one, how many 2's should I have?
5.
I should have 5 2's being multiplied together. It's not 2 times 5, which is 10. It's 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32. So 2 to the 5th power is 32, not 10. And then the last one is going to be, we can say 5 to the 2nd power or 5 to the power of 2, but squared. Squared is typically what we want to say because, again, when you're dealing with volume, you have squared, or sorry, not volume, area. When we're dealing with area, you always have squared units. So it could be square feet or square inches. You've heard those phrases before. So whenever we have 2 in the exponent position, we are talking about squared. Okay, we are now going to start in our book at lesson 1.2. The title is Powers and Exponents. So everybody can turn with me to page 9 so that you can see what we are working with. Right here, because at the bottom of page 10 in your book, you have in-class practice. So I went ahead and put them in this form for you. So we're going to work these 3 together. So I'm going to write the product as the power. I'm going to have you go ahead and try those 3. And then we're going to talk about them. Okay, number 1 and 2 are pretty easy, right? You could do those pretty quickly. Okay, so what's number 1?
15
To the 4th power. And 6 is, or number 2 is 6 to the 6th power. Okay, number 3, it just mixed it all up. So instead of having just one digit repeated over and over, it has 2 numbers repeated a couple of times. So how many times do you see 13 show up there? 3. So it'd be 13 to the 3rd power times, what do you think I'd write next? 7 squared, because there's 2 of them. Okay, so on this one, all I'm doing is I am just combining my numbers that are alike. So I'm going to take my 13s, I'm going to make it 13 cubed times 7 squared. Now it says, explain your reasoning. Okay, what is that showing? What is that showing? Does it matter if I put it this way? Does it matter if I put 7 squared times 13 cubed? Does it matter? It doesn't really matter because it's being multiplied, right? So multiplication is commutative. You can flip-flop them. You can put 7 squared first and then 13 cubed second. You can say 7 squared times 13 cubed and you're still going to get the same answer. Because what's 7 squared? 49. You're still going to be multiplying 49 times whatever 13 cubed is. Okay, and you're going to end up with the same answer. Yes?
I just did 13 to the third power, well, I just put, instead of 7 to the or 7 cubed, I just put 14.
But got to be careful because it doesn't mean 7 times 2, it means 7 times 7. Whenever you see 7 squared, it's 7 times 7, which is 49. So you just have to be really careful about that. Okay, so looking at number 4 and 5, you're actually finding the value. So I went ahead and wrote up there what you're expanding it out to look like, and you're just going to start solving it. We know that 6 times 6 is 36, but I got to multiply that number by 6 also. So what's my answer?
116.
216. 216. And then 9 squared is 81, not 18. Okay. Give me a thumbs up or a thumbs down. How did we do on those two? Okay, so far so good. All right, moving over. Determine whether the number is a perfect square. Is 25 a perfect square? Yes. Is 99? No. Okay, but your friend says that 20 is not a perfect square because 4 squared is 16 and 5 squared is 25. Can you complete that friend's reasoning? Think about your base numbers for a second. You have a base number of 4 and a base number of 5. Is there a whole number between 4 and 5?
No.
No. So that's why 20 cannot be, because if we know that 4 squared is 16, 5 squared is 25, there's not a whole number between 4 and 5 that I can square to give me 20. Okay?
4.5.
So we would say there is not a whole number between 4 and 5 to square. Does that make sense?
Yes.
Perfect squares are made up of whole numbers. Okay, so you have to have like, it's got to be 8 and 8. It's got to be 12 by 12. It can't be 12 and a half by 12 and a half. It's got to be a whole number. Okay, let's look at practice page. Okay, yesterday we defined these 3 vocabulary words in our glossary section of the journal. We have a power. A power is a product of repeated factors. The base we talked about a little bit ago on our little notes page. The base of the power is the repeated factor. It's the big number. The exponent is the little number of the power, and it's the number of times that the base is going to be multiplied by. Okay, so we have some different examples. We have 3 to the second power. We usually read it as 3 squared. Then we have 3 to the third power, which is typically read as 3 cubed. We have 3 to the fourth power and 3 to the fifth power. Okay, so you read them after it starts. Once that exponent turns to a 4 or greater, you just say to the power of 4 or to the fourth power. Does that make sense? Okay. All right, here we go. Looking at the first example, it's asking us to write each product as a power. So all we're doing, it's very similar to our notes page we did just a second ago. We are going to show the power of the expanded form. So it's giving us expanded, the mathematically how to solve it. You're going to condense it down to the power. So it would be 7 to the 5th power. B, 12 cubed. Okay, and then C would be 100 to the 6th power. All right, let's look at our example 2. Now we're actually finding the values of powers. So this time we're going to actually work it out and find the value. So these two examples already have them done for us. 7 squared is 49. 5 cubed is 125, not 15. It's 5 times 5, which is 25, times another 5, which is 125. The square of a whole number is called a perfect square. Kind of like that example with the cans and the investigate, how each layer was a perfect square. 9 times 9, 8 times 8, 7 times 7. Those are considered perfect squares. Okay, example 3. We're determining whether each number is a perfect square. A, 64. Yes, because what makes 64?
8 times 8.
8 and 8. They are a perfect square. Picture that visually. If I have an 8 by 8 square, it's a perfect square because the sides are the same. The dimensions are the same. B would not be. And C, yes, because it's just a 1 by 1. So it would be a perfect square. All right, so let's go ahead and try 4, 5, 6, 7, and 8 on your own, and then we'll check it. Our last page today. Okay, it says that you can use powers to find areas of squares. So we kind of talked about that a little bit, and it was kind of similar to... All right, it's a little similar. Just leave it open. And when you leave here, leave it open so it dries because it's just water. Okay. Okay. Example 4 is giving us information from a survey. It says a researcher asked 100 people what type of movie they prefer. The data shows the responses. How many people said that they prefer action movies? So it's breaking it up, and it looks kind of like the area of maybe like a floor or something, the way that they have all the data displayed. It says that each grid square represents one response. The action section is a square with a side length of 6 units. Do you see it? It's purple, the action piece. Okay. Find its area. So if I have a 6 by 6 square, then the area of action is representing what?
36.
36. So then 36 people prefer action movies. Okay, do you see how they displayed that data? Okay. In example 4, how many people said that they prefer comedies? This is on your paper in your journal. So looking at comedy, here it is, it's blue. It's 2 by 2. So how many people prefer comedy?
4.
4. So number 9 in your journal should be 4. Number 9. Yep, you're just going to write 4 by number 9 in your journal. And then number 10.
Should we label it and do 4 people?
You can. Number 10 says the die in the shape of a cube. Or the die is in the shape of a cube. The total area of its face is 1,536 square millimeters. What is the side length of a face of the die? Explain. Okay, so we're looking at this picture of the die right here. How can I figure out the side length of one face of the die? What would I do, Ruby? By 6? Okay. So the area of one face would be 1,536 divided by 6. Does everybody agree?
Yes.
Yeah, because there's 6 faces. They're all equal. So if I do that math and I divide that by 6, then I end up with 256 millimeters squared. But that's the area of one whole face. So then what do I do?
Time it by.
Because I only want to know the side length, right? The side length. So I know this whole thing, this whole face right here, I'm going to change my colors. This whole face is solved by doing 1536 divided by 6. Okay, if I do that, I'm just going to save us time because we're running out of time. It's 256 millimeters squared. Okay, but I only want to know one side length. So this times this equals 256. Did we do that earlier? Did we see a number like that earlier?
We gotta divide that by 4.
We saw one close. We know 15 times 15. Do we know 15 times 15?
125.
It's 225. So I'm getting closer. What do we want to try? 16? 16 times 16? Would that work? Yes, it does. So one side length is going to be 16 millimeters. It is a perfect square. So if I do 16 times 16, I end up with 256 millimeters squared, which is the area of one face of the cube. Okay, we're going to start our lesson today.